Team24, and our project is about ride wait times at Walt Disney World. So here at the problem box, this is what got us interested. Every ride at Disney World has a sign out front showing the wait time, and that is the number of people use to decide what to do next usually. The thing is that number is not actually measured. It is Disney's own estimate, put together by a method they do not share publicly, and it is widely believed they set it a little high on purpose so that when the line moves faster than the sign says, you walk away happy. There's actually a whole set of paid apps and websites that exist just to give visitors a better estimate than the free one on the side, which tells you people do not trust that number. And the stakes are real. Millions of people visit each year, and they are constantly making small decisions based on these signs, like whether a ride is worth getting in line for right now or come back later. On top of that, the wait time is basically a stand-in on how crowded the park is. Disney now sells passes that let you skip the line with prices that move up and down with demand, so predicting wait times well is worth real money, not just convenience. So we set our answer 3 questions. First, what actually explains how long the wait is on a given day? Second, how big is the gap between the posted number and the real wait, and does it change with the season? And third, can we forecast tomorrow's wait accurately, and can we beat a simple guess? So here's our data. For our data, we use a dataset from touring plans. It has a timestamp posted waits and actual waits that volunteers recorded by timing themselves in line, and a separate daily file with information from each park, like the season, holidays, and weather. We picked 3 rides on purpose so we could have some contrast. Seven Dwarfs Mine Train, which is a headliner for Magic Kingdom with famously long wait times averaging around 85 minutes. We also chose Pirates of the Caribbean, a big indoor ride that moves people quickly and averages under 30 minutes, and the Safari Ride, an outdoor ride of Animal Kingdom we figured might be sensitive to the weather. We took all those readings and boiled them down to one average wait per ride per day, so it lines up with the daily calendar and weather. Cleaning up actually mattered here. Disney codes a closed ride as -999, and there were a handful of clearly broken entries, including one actual wait recorded in -92,000, which is obviously an error. We dropped those, which was about 7 to 8% of the readings, and then we merged in the season, holidays, events, and temperature. We kept 2015 through 2019, which is before COVID shut down the parks, which left us with about 3,600 ride days. For methods, we built up the same way we did in class. We start with a simple regression on one variable, move on to a multiple regression with several, check the model with diagnostics, and then switch to series models for forecasting. Just as a warm-up, we ran a simple regression of the weight against temperature of the outdoor ride, and it came out negative. Every extra degrees goes with a little under 1 fewer minute of wait. That sounds backwards until you realize the hottest days in Florida are slow late summer seasons, so temperature is really standing for how busy the calendar is. On its own, it only explained about 40% of the variation, which told us we needed more than one variable, which Garija was going to take it from here.
Thanks, Jacob. So this table is our multiple regression, run separately for each of the 3 rides, and every number is in minutes of wait. The pattern is pretty consistent. The 2 things that matter most are the ticket season and whether there is a special event that day. On Seven Dwarfs, moving from the cheapest season to a peak season adds about 14 and a half minutes to the average wait, and a regular season adds about 5. You can see the same shape on the other rides. Meanwhile, weekends and holidays barely move the needle once the season is in there, and temperature only has a small effect. So the big story is that the calendar drives the crowds more than the weather or the day of the week can. There is one honest wrinkle worth pointing out. The event flag comes out negative at 2 of the Magic Kingdom rides, but positive at Animal Kingdom. That is not a contradiction. It is because the flag is tagging different kinds of events at different parks. An evening party can actually pull people out of the regular line at one park while a festival packs another. So we treat that variable as the least trustworthy one. We also checked that the predictors were not stepping on each other, and they were not. So multicollinearity was not a problem. Our R squared values land between 17 and 29%, which is honestly what you would expect, because a huge amount of what makes one day busy is just random. Now, checking the model is where we found the thing that shaped the rest of the project. When we looked at the leftover errors, a couple of formal tests flagged mild problems. The errors were not perfectly normal and the spread was not perfectly even, which is common with this kind of data. But the important one was autocorrelation. Our Durbin Watson numbers came out well below 2, which is the telltale sign that today's leftover error is tied to yesterday's. In plain terms, busy days cluster together. That matters because it means that the regression's confidence intervals are a little too optimistic. So we are careful not to oversell borderline results. And it is the specific reason we did not stop at regression and moved on to time series models, which are built for this exact kind of day to day dependence. Okay, so now my favorite part, the gap. This is where we compare the posted numbers to the actual weight people recorded. On average, across the three rides, Disney overpredicts by about 23 minutes, and it is not flat. It grows with the crowds from about 19 minutes in the cheap season up to about 28 minutes in the peak. It is also dependent a lot on the ride. On Pirates, the fast indoor ride, the gap is only about 9 minutes. On Kilimanjaro, it is about 18. But on Seven Dwarfs, the big headliner, the posted sign is inflated by about 45 minutes on average. So the more popular the ride is and the busier the day, the more the sign oversells the wait. Abbas is now going to take us into the forecasting.
Thanks, Girija. Our last question was whether we could forecast the next day's average weight, and this is where the time series work comes in. We focused on Seven Dwarfs as it has the longest, richest series. The first thing we did was decompose it, which just means splitting the daily weight into a slow-moving trend, a repeating weekly pattern, and whatever is left over. The weekly pattern was clear. There was about a 14-minute difference between the busiest and quietest days of the week. That regular rhythm is a big part of what makes forecasting possible. Then we set up a real test. We held out the last 90 days, trained on everything before that, and asked each model to predict one day ahead across that window. We compared three approaches. The first is a simple baseline that just repeats the value from the same day 1 week earlier. The second is exponential smoothing, specifically Holt Winters, which tracks the level, the trend, and the weekly pattern. And the third is an SAR IMA model, which is the seasonal version of the Box Jenkins approach from class. Here's how they did. The simple repeat last week baseline was off by about 16% on average. Both of the real models cut that roughly in half. The SAR IMA model got down to about 10%, which works out to an average miss of only about 8 minutes, and that is about a 40% improvement over the baseline. Holt Winters was basically tied with it. And if you look at the chart, you can see the forecast line hugging the actual series pretty closely across those 90 days. There is one caveat we want to be upfront about because it is interesting. This advantage only holds when you forecast one day at a time. We also tried forecasting all 90 days at once, and there the smoothing models drifted off and the simple baseline actually won. So these models are genuinely useful for planning tomorrow, but they are not built to tell you what the weight will be 3 months from now. So, pulling it all together, here is the bottom line. The posted sign is high by about 23 minutes on average, and it is worst exactly where it matters most, on the most popular ride during the busiest season, and a simple model that uses only information you would already have the day before can predict the real weight to within about 10%, which beats trusting the sign. So a fairly basic forecasting model is a better planning tool than the number Disney puts in front of you. We also want to be clear about what we cannot claim. The actual weight data comes from volunteers timing themselves, so it is sparse, and the gap numbers carry some noise because of that. The autocorrelation we mentioned means our regression error bars are a little too tight. The data stops in 2019, and so it is before Disney's newer Genie Plus and Lightning Lane system, which may have changed both the crowds and how the signs are set. And we only looked at 3 rides at one resort, so we would not push these exact numbers onto other rides without refitting. If we kept going, we could use models that handle the autocorrelation directly. We would forecast the gap itself so a guest could see a corrected estimate on their phone. And we would extend the data to more rides and to the years after 2020. That is our project. Thank you very much for watching, and we are happy to take any questions.